Good day to all lecturers. We are students from Group 1-5 and we are going to present the Integrated Design Project for January 2022 semester. Our group members are Darius, Xin Ying, Joy, Azalia, and Zhafran.
Hi, I'm Azalia. In Chapter 2 CEB 2040 Reaction Engineering 1, these are the topics that will be discussed further on our video. Are you ready? In this chapter, our main focus will be on relating the knowledge of Reaction Engineering 1 to the steam methane reforming process in the production of hydrogen gas. It consists of two main reactions, which is an endothermic reaction in an SMR reactor and an exothermic reaction in a WGS reactor. Because of the efficiency at high temperature and pressure, PBR are often ideal for these processes. Furthermore, because the catalyst is present in both processes, the steady-state operation can have a high conversion at a high reaction rate, generating more hydrogen than other catalytic reactors. Hence, in order to design H2 production of 30,000 tons per year with a purity of 99.9% and in accordance with the knowledge and principles of Reaction Engineering 1, we have designed a steam methane reforming process with suitable reactors and appropriate designing.
Hi, my name is Darius Bong and I will be explaining the natural gas steam reforming process for reaction engineering. Steam methane reforming is one of the most common processes for hydrogen production. The natural gas stream is first purified to remove other components besides methane, which is the hydrocarbon to be used in SMR for this case. Then it is mixed with a stream of steam in a mixer before being fed into a packed bed reactor with a catalyst to enhance the reaction rate. As the product stream exits the reactor, it is cooled before being fed into another packed bed reactor for a high temperature water gas shift reaction to remove the harmful carbon monoxide in the product stream to obtain carbon dioxide. Since the temperature at which the water gas shift occurs is still significantly lower than the temperature for SMR. For both SMR and water gas shift processes, packed bed reactors are chosen as they have high conversion rate per weight of catalyst, they are easy to build, and they provide more contact between reactants and catalysts, which enhances product formation, and they are also effective at high temperature and pressures, which is relevant for steam methane forming. Next, for the kinetic data of SMR process, the chemical reaction would be as follows. 1 mole of methane reacts with 1 mole of steam to produce 3 moles of hydrogen gas and 1 mole of carbon monoxide. The reaction occurs at a temperature of 999.5 degrees Celsius or 1272.65 Kelvin and at a pressure of 30.5 bar. The reaction is assumed to be first order and the catalyst used will be 18 weight% nickel oxide or aluminum oxide. For the assumptions for SMR process, we assume steady state flow, pseudo first order reaction as steam is in excess, steam to hydrocarbon ratio is 2.226, natural gas stream is purified to methane and has a flow rate of 634.196 kmols per hour. Steam stream has molar flow rate of 1411.597 kmol per hour and the reactors are isothermal. The reactor volume is assumed to be 7,853.982 meter cube and requires 86.02 kilograms of catalyst. Next, for the kinetic data of water gas shift process, the chemical reaction would be as follows. 1 mole of carbon monoxide reacts with 1 mole of steam to produce 1 mole of hydrogen gas and 1 mole of carbon dioxide. This reaction occurs at a temperature of 570 degrees Celsius or 843.15 Kelvin and at a pressure of 29.86 bar. This reaction is assumed to be first order and the catalyst used will be iron oxide and chromium oxide. For the assumptions for water gas shift process, we assume steady state flow, first order reaction, and that the catalyst used is iron oxide and chromium oxide. High temperature water gas shift is carried out and reactors used are isothermal. The reactor volume is assumed to be 125.075 meter cube and requires 1.51 times 10 to the power of negative 6 meter cubes of catalyst. To maximize selectivity and yield of hydrogen in the two reactions, the Chatelier's principle will be applied for this. First, we increase the temperature for the SMR reaction as it is endothermic. This would shift the equilibrium to favor the forward reaction to remove the excess heat. The reverse is applicable for water gas shift reaction where we decrease the temperature as it is an exothermic reaction. This would shift the equilibrium to favor the forward reaction to produce more heat and products in the process. Lastly, the feed entering the SMR reactor should have higher concentration as this would favor more production of products.
I'm Zhafran. In Chapter 3, CEB 2053, Process Modeling and Simulations, there are topics that will be discussed further on our video. In this chapter, a simulation has been done using symmetry software where Advanced Bank Robinson is chosen as the thermodynamic package, and throughout the chapter, the knowledge from CEB 2053, Process Modeling and Simulations, will be applied, using the data and result obtained from the simulation as well as the data from the manual calculations. Data validation has been performed to determine the deviation error based on the comparison.
Azalia again here. Firstly, we have performed a simulation of the steady-state reaction using symmetry software based on the process parameter from Chapter 2. The components involved are water, methane, hydrogen, carbon monoxide, and carbon dioxide. After both inlet streams are mixed, the mixture is channeled into the first reactor, which is the SMR. Since high temperature gas shift is carried out and the outlet temperature leaving the SMR reactor is low, a heat exchanger with a high pressure steam is used to heat up the mixture before entering the following WGS. For both reactors, a set of equations have been derived. After listing out the possible assumptions, we started deriving for the mass balance. Then after defining the rate law, we have derived component balances for all species involved in the reactors. After the simulation has been run in the symmetry software, we recorded the result of the total flow rate and the flow rate for each components for both reactors. The value of the manual calculation and the simulation were compared, and the deviation error between the two data is around 18%. This is applied for both reactors. The cause of this large deviation error may be mainly due to the assumptions made during the manual calculation, which cannot be applied in the simulation process. For example, in symmetry, both reactors cannot be assumed isothermal because there will be temperature change between the inlet and outlet streams. Besides that, there is limited catalytic flow reactor in symmetry where there is only plug flow reactor. In the manual calculation, however, the formula involving packed reactors have been used.
Next is the effect of pressure on the reactor performance. As the pressure increases, the mole fraction of hydrogen at SMR and WGS outlet stream also increase. This can be explained as the pressure is applied to the system, more molecules will be colliding with each other, producing more products. Next is the effect of temperature on the reactor performance. The increase in temperature causes the mole fraction of hydrogen to increase at the SMR and WGS outlet stream. This can be explained as the temperature of the system will have effects on the kinetics of the molecule. As the temperature increases, the collision frequency of the molecule will also increase, thus causing more reaction to occur, causing more products to be produced. Next is the effect of flow rate and composition on the reactor performance. As the mole flow rate of natural gas streams and the mole fraction of methane increases, the mole fraction of hydrogen at SMR and WGS outlet also increase, but this cannot be the same for the increase in mole fraction of methane at certain point. A mole fraction of hydrogen at WGS outlet started to drop from 0.4885 to 0.4739. Le Chatelet principle states that a stress is applied to a reaction mixture at equilibrium, the net reaction goes in the direction that relieves the stress. According to Le Chatelet principle, the position of equilibrium will move away in a way that opposes the changes that was made to the system, which is to favor the production of the product. Meanwhile, the value of the mole fraction of hydrogen at WGS drop as the system starts to favor to the reactant side.
Hi, I'm Xing, and I'm going to explain the first part of separation process 2, which requires students to design an adsorption system to produce hydrogen with 99.9% purity. For your information, hydrogen is an ultimate renewable fuel due to its sustainable characteristics such as clean and low carbon emissions. Hydrogen can be produced from a large variety of resources, particularly natural gas, by employing steam methane reforming technology coupled with pressure swing adsorption system or PSA. A 2-bed 6-step PSA system is selected to extract hydrogen from the SMR of gas, which consists of 76% hydrogen, 20% carbon dioxide, 3.5% methane, and 0.5% carbon monoxide. PSA system is an ideal separation method as it can be applied for a relatively large range of temperature and pressure settings. For this adsorption system, activated carbon and zeolite 5A are chosen as adsorbents. Besides, the adsorption column has a height of 2 meter and a diameter of 0.38 meter, with a carbon to zeolite ratio of 70 to 30. Stainless steel is selected as construction material for the adsorption column due to its high resistance towards corrosion. Furthermore, The PSA separation system operates at optimum conditions of 298 Kelvin and 1 bar. Also, a purge to feed ratio of 0.11 is chosen for the dissolving impurities on the absorption bed during regeneration step. In the adsorption bed, there is a major section where most of the concentration changes happen, known as mass transfer zone or MTZ. Breakthrough curve for activated carbon and zeolite 5A can be obtained to determine the length of MTZ when the whole bed in the absorption column is fully saturated. Since the calculation steps are the same, we will take MTZ of activated carbon as example. From the breakthrough curve, the breakpoint time, which equals usable capacity, is at 8 minutes. Meanwhile, when C over C naught reaches 0.50, the ideal adsorption time is equivalent to total capacity, which is 23 minutes. By multiplying TU over TT with the length of carbon of 1.4 meter, the used bed length will be obtained. Lastly, the MTZ for activated carbon can be calculated by subtracting total bed length with used bed length. The mass transfer zone for activated carbon and zeolite 5A are 0.9130 meter and 0.2444 meter respectively. Now, I will pass the floor to Xin Ying.
Hi, I'm Lim Xin Ying and I will continue to explain the second part for separation process 2. In this PSA system, industrial track granular activated carbon with an average pellet size of 1.15 mm and sphere tight zeolite 5A with an average pellet size of 1.57 mm are selected as adsorbent. For H2 enrichment unit, activated carbon will be utilized as primary layer to intercept CO2 and followed by zeolite 5A layer which will absorb CH4 and CO. Two isotopes are selected for activated carbon and zeolite 5A respectively. Dual side LAMO DSL model with the formula shown is selected for activated carbon. For H2, the SL model against adsorption of gas on activated carbon has the best fit of data. The value of R squared is 0.9999. For zeolite 5A, loading ratio correlation LRC model with the formula shown is selected as the best fit of data on zeolite 5A is obtained with the R square value 0.9995 for H2. 5 strategies are recommended to achieve 99.9 purity of H2 production. Firstly, the adsorption time should be shortened. When the time increases, the adsorbent bed will be partially saturated as part of CO2 trap will escape and mix together with H2, giving rise to a drop in H2 purity. Besides, the pressure equalization time should be increased. This is because the impurity in feed gas that flow to the regeneration bed take time to be fully absorbed before pure H2 being produced through the product end. In contrast, the pressure equalization step should be decreased. This can be proved through the graph shown. Furthermore, a lower feed flow rate is recommended. This is because the time of Xing gas staying in the adsorbent bed to contact with the adsorbent will be shortened. In addition, the pure to feed ratio should be increased to ensure a greater number of impurity in the bed can be dissolved and flow out with the pure gas. For the desorption or regeneration process, by decreasing the pressure of PSA system until close to atmospheric pressure, the solid adsorbent can be purified from the impurities. Pure hydrogen is used during the concurrent depressurization or blown down. Tail gas that contain dissolved gases will exceed the bottom of adsorption bed. The adsorbent bed will be further pressurized after desorption is done. In conclusion, we have successfully designed a system to produce 30,000 tonnes per year with 99.9 purity of hydrogen via steam methane reforming SMR technology. We are going to proudly mention we can beat the tender from REX Energy STM PhD with our design. This is because we have done research on each part in order to stimulate the steady-state reaction process. Besides, various strategies related to maximize the selectivity and yield of hydrogen, minimize the side reaction, as well as achieve 99.9 purity of hydrogen production and desorption process are recommended with relevant and valid reference. Through all the recommendations given, we learned that every part is important to ensure successful design and performance of system. Only with the collaboration of 3 courses, we can succeed in our aim. If we are given a task to design a project, we strongly believe that we are capable in designing our type of projects and improving the performance of the design.